Okay, so hi, I'm Jan. I work for Polkadot at Parity, and today I'm here to tell you about PolkaVM, which is our new RISC-V based virtual machine. So first, a little bit of history. Since the very beginning, Polkadot was essentially built on WebAssembly. In particular, one of our unique features is that our state transition function, which we call a runtime, and which essentially contains all of the business logic of the blockchain, is a WebAssembly program that we can just dynamically upgrade in easy, forkless upgrades. And also our native smart contract solution is WebAssembly based. So we're very much heavily invested in WebAssembly, and we care a lot about its speed. In hindsight, I think picking WebAssembly was absolutely the right choice here because there weren't really any other good alternatives back then. And in general, we are happy with it, but there are some problems. For example, WebAssembly is actually pretty complex. There's no stable baseline and it's constantly growing. The very first minimal viable product of WebAssembly had 172 instructions, and that's up to over 400 today. So that's quite a bit of growth. And if we count all of the current proposals which are in flight, we get up to 541 instructions. So this is quite complex. For comparison, if we look at the current king of complexity of instruction sets, which is the 64-bit x86 architecture, it has, depending on how you count, 2,000 instructions. So WebAssembly is 1/4 of that. That's a lot. And compilers are gradually starting to use those new instructions by default, often with no prior warning. Like, for example, most recently, the sign extension instructions were enabled by default in LVM, which did surprise multiple blockchains, including us. It's also not 100% deterministic, and if you have a blockchain, you do very much need 100% determinism. It's an absolute requirement. The exact bit patterns of floating point, not a number, values are unspecified, and the size of program stack is unlimited and might overflow, among other things. So it's not a total deal breaker because you can work around this, but it's really annoying. And WebAssembly is a pure stack machine, and real hardware is not. So this means that when you want to execute a WebAssembly program in an efficient manner, you need to reduce it into a register machine. And register allocation is an NP-complete problem, which basically means it's really hard and it's really expensive. So it's hard to have fast execution and fast JIT compilation times with WebAssembly. So can we do better than that? Ideally, we would like an instruction set which is like a register machine. So it's easy to run on real hardware. It's simple and has a stable baseline and doesn't change underneath us by itself. It's portable. It's well defined and standardized. It's already widely supported by compilers. We do not want to maintain our own toolchain. That's something we absolutely don't want to do. It's guaranteed to be supported into the future. We're looking at timescales of like 10, 20, 30 years. Has enough features to compile arbitrary existing programs, but it doesn't force on us features which we don't want or need. So wait a minute, doesn't that sound just like RISC-V? And yes, exactly. That's what we were thinking when we surveyed this whole landscape of alternatives to WebAssembly. So we decided, hey, let's try a new VM and see how it goes. So the very first prototype for PolkaVM or new RISC-V based VM was written in only 2 days. Granted, those were very long 2 days, but it were 2 days nonetheless. And it was a full JIT recompiler which recompiled the RISC-V code into fully native code. And the funny thing is, this prototype written in 2 days was already faster than some of the production VMs used today on some of the chains. So we were like, this looks really promising. Let's try and go all the way in and see how far we can take this. And here we are today. PolkaVM is still a research project, but it's slowly approaching production ready status. And the current version already achieves state-of-art results on several metrics, and we're not done yet. So execution performance, this is how fast one of our benchmarks runs. And on the very left, we have native. Also, keep in mind, this is logarithmic scale to make the graph readable. This is not linear. So on the very left, we have native. This is essentially the benchmark executed natively just on bare metal on the CPU, right? And we have 3.8 milliseconds, quite fast. And in the second place, we have PolkaVM 5.7 milliseconds, so almost native performance. And in the third place, we have WASM time, which is essentially the gold standard for WebAssembly VMs. And this is the WebAssembly VM we are currently using. So we are already slightly faster than the WASM time, which is quite amazing, because PolkaVM has been in development for only a few months, and WASM time has many years of effort put into it, and it's very well optimized. So these are great results. In the fourth place, we have WASM single pass, and this VM is notable for the fact that it's essentially, unlike WASM time, it guarantees linear time single pass compilation. So this is, for blockchains, this is very good for security, because you cannot then denial of service attack the chain with a special crafted program. Then we have Solana RBPF. They're using eBPF as their instruction set, and their performance is not that great. And in the last place, we have WASM, which I put it here just for comparison, because this is an interpreter written in pure Rust. So this is essentially as fast as you can go, more or less, with an interpreter without any assembly tricks. So this is great, but this is only execution performance, and we also care about compile time performance. So how long does it take to translate a program from RISC-V into native code? And we're already we're also pretty good here. We are in the first place with 427 microseconds, and the second best is Solana. Might not be that great, but they have really fast compile time, so that's something they got right. And on the very far right, we can see WASM time, which is pretty slow when compiling. So this is how they get their stellar performance. They just have a really powerful optimizing compiler, which takes quite a long time. So PolkaVM features as of today. We essentially execute as fast as WASM time, but we are over 160 times faster to compile. We compile faster than Solana while being over 12 times faster executing than them. We guarantee linear time compilation, so you cannot denial of service the VM by crafting a specially malicious program to blow up the compilation times. We guarantee 100% determinism out of box, so you don't need any workarounds to make sure the execution is deterministic. We are secure and sandbox by default. This is something that I haven't seen any other VM do. Most other VMs just run their guest programs within the same process and hope they are secure, which usually works, but bugs happened. So we took a different approach. We assumed that we have bugs. So we always run guest programs in another process. So if it misbehaves, it cannot do anything malicious to the host. We also run them in another namespace. This is essentially exactly the same technology as Docker uses. So the guest program, even if it breaks out of the sandbox, it cannot access the network, it cannot access the file system, it cannot access any other processes because it's fully namespaced, just like Docker containers are. And our guest programs also run under a strict seccomp sandbox. What this does is basically it blocks the vast majority of syscalls, which are essentially calls into the Linux kernel to request some servers from the operating system. And you have something like, I don't know, 200, maybe 200 of them in total. So we actually need only, I think, 6 of them. So we block all of the rest. And this is quite important because most of the kernel exploits actually happen through some obscure syscalls that are not commonly used. So this reduces the attack surface quite considerably. And we can also run arbitrary C, C++, and Rust programs, which is not true, for example, for Solana's VM, which has quite severe limitations on what you can run there. But that's not something I will elaborate here. Oh, and we also have really fast gas metering. Gas metering is essentially a feature that you need for things like smart contracts, right? And we implement essentially two kinds of gas metering: synchronous gas metering and asynchronous gas metering. And the difference between them is quite simple. With synchronous gas metering, before you execute a piece of code, you essentially consume the gas and check whether you are out of gas or not. If you are out of gas, you abort the execution. If you still have gas in the tank, you continue, right? So asynchronous gas metering removes the check for the gas, and gas is instead checked from another thread running concurrently with the program. So this makes it a lot more efficient. And for the majority of use cases like smart contracts, you don't actually need synchronous gas metering. So you can have this essentially free performance uplift for like with no downside essentially. And the funny thing is, when we are running with gas metering, we are faster than WASM time, which is running without gas metering. And our gas metering in general is faster than theirs. And okay, so our VM can do quite a lot. Can run Crysis? Not yet, but it can run Doom. I have ported Doom to our VM, and it runs fully within the VM, including the graphics and the sound. Everything except I/O, obviously. So input, output, you cannot encapsulate that fully within the VM because the user has to interact it with somehow. But everything else runs inside of the VM, and you can play through the whole game like this. Here's a link. You can git clone the repo and play it yourself if you want. And we also run Doom on our CI. So on every commit, we actually check that Doom still runs and that it works correctly. So we are probably the only VM in existence which runs Doom on its CI. So what's our secret sauce? Like why we have managed to achieve these results in only a few months of work? So Our first secret sauce is RV32E. This is an embedded variant of RISC-V with only 16 registers. But in reality, it's only actually 13 because the zero register doesn't really count, and the compiler by itself doesn't emit code which uses the GP and TP registers. It was quite recently ratified in January of this year, and the toolchain support is not there yet, but hopefully soon it will be. And this is perfect for a recompiler into an instruction set like 64-bit x86, which only by itself coincidentally has 16 general purpose registers. And this is because we can essentially map every RISC-V register one-to-one to a native register. So this makes code generation really, really simple, because you don't need to spill any of the registers into memory. And it also allows the compiler to essentially optimize the code for 16 registers. Our secret sauce number 2 is the sandbox. This is not just for security, actually. We have a specially crafted ELF file which the VM launches, which guarantees that the lower 4 gigabytes of address space of the process are free and can be used by the guest program. And this has the magic property of allowing us to have really cheap single instruction memory accesses. So here we have 2 bits of assembly, one generated by PolkaVM and one generated by WASM time. So as you can see, we can do this in one instruction, and WASM time needs 3 significantly more complex instructions. So this makes it quite a bit faster to access memory. And our secret number 3 is our compilation pipeline. Basically, we do not, the VM doesn't actually load the files that a compiler spits out. What we do is that we use a standard toolchain, so your standard RISC-C, Clang, or GCC, and we compile the program into a standard ELF file. And then what we do is we have our own linker, which takes that ELF file and post-processes it. So this linker does things like it does relocations. So now we don't have to do relocations in the VM, the linker does it. It does macro op fusion. So basically in RISC-V, for example, if you want to load an immediate value into a register, if the immediate is too big, you need 2 instructions. But we are a VM, we don't have such limitations. So what we do is that we merge those 2 instructions into a single one. So that's essentially macro op fusion. And we do this in the linker. So the VM by itself doesn't have to do this. We also do some other minor optimizations like extra inlining, constant propagation, dead code elimination, etc. So the general idea is to move as much complexity as we can into this linker and keep the VM as simple as possible. So the linker runs offline and generates a program blob, which then the VM can load and generate native code. And this works quite well. And so what about the future? We are not done yet. We're planning even more performance improvements. Ideally, we would like to be as fast as native code, as natively compiled programs. We may or may not get there, but we will certainly try. And there are quite a bit of things we haven't tried yet. So even more macro fusions. So we're currently fusing essentially only immediate loads, but there are quite a bit of other macro fusions which we could be doing, which could improve performance. There are also a bunch of other RISC-V extensions which we could implement. Currently, we're just supporting the M extension, which is the multiplication extension, and besides that, we are plain vanilla baseline RISC-V. So there are quite a few interesting extensions, like the bit manipulation extensions, which were ratified some time ago. There are those T-head extensions. They are vendor specific, but some of them are very interesting, and we think they might improve performance quite a bit. And we also want to add 64-bit support, because we're currently only 32-bit. We're also planning on adding even more features, like dynamic link of multiple programs at runtime. Time travel debugging is also something we want to have, which, as far as I know, no other VM supports. Basically, what is time travel debugging? When you're debugging a normal program in a debugger, you can only go forward, but with time travel debugging, you can also go backwards. So this is really cool. This is a really cool debugging feature, and thanks to the fact that we are 100% deterministic, this should be quite easy to implement. And we also want to support running on other CPU architectures, because right now we're only supporting 64-bit x86. So the major candidates here are 64-bit ARM, namely the M1 Apple Silicon chips. We want to be able to run on them. And of course, native RISC-V. RISC-V is not there yet with hardware, but maybe in the future, when we will have really high performance RISC-V servers, we want to be ready for that. Also, we also want to do some research on coming up with better cost models for gas. So we want to figure out if we can lower the gas fees by more closely modeling how modern CPUs work, which is something that we think is a worthwhile research direction. Also, we do want to write a proper spec for the VM before hitting version 1.0. So we want to have a comprehensive test suite as part of the spec, which will be independent from the VM, and we want to make it really easy for someone else to just implement a new VM that is 100% compatible with ours. And this will also help with long-term support and stability. So that's all I have for you today. Thank you. You can check out the code at the following link. You can also, if you want to talk about this, you can message me on Element, or you can just email me. And that's all from my side today.